lecture in which a prominent expert in the underlying subject is supposed to explain an aspect related to the program in a way accessible to research mathematicians. And we are very fortunate to have today Chus Sanz-Serna. Chus holds the Chair of Excellence in Mathematics at the University of Carlos III in Madrid. He's also a professor of mathematics at the University of Valladolid, where he spent most of his career and where he was a president for 2 terms. But perhaps most importantly, he is one of the people that shaped modern computational mathematics, and he is known for 2 monumental steps. One is the theory of symplectic methods for Hamiltonian problems, and the other one is modern methods for stochastic systems. And today we will join the 2. So, Chus.
Thank you very much. I am very thankful for the invitation, but also I am very thankful to Arye, who flew last night from Hong Kong, so he must be pretty tired by now, and yet he's made the effort to think of an introduction that is not true, but is very kind to me. So I decided to speak about this topic because it's something where you see the use of geometric integration, and you see it combined with a number of ideas from very different fields in mathematics, or even very many fields in science. So I'll start with handling probability distributions in prehistoric times. Well, usually prehistoric means things that happened before there is a written record. Now for mathematicians, at least for people in computational mathematics, prehistoric means things that happened before computers were available. So for us, history only starts some 70 years ago. So whenever you have to work with the probability distribution, then you need to compute integrals. There's the mean, or the expectation, and the variance. But also, if you want to know the probability that the random variable is less than a, you have to compute the integral of the indicator function. So it's of the essence to be able to, if rho is the density function, it is of the essence to be able to compute things like that for suitable functions f. And before computers were available, those integrals were calculated once and for all, in general by numerical quadrature, but there were other devices. And once they had been computed, you could sell them in tables like this. This is student t distribution. It has a parameter that ranges from 1 to 1,000, and the columns are values of the probability of being between -infinity and the number given there. So you see this use of tables has clear limitations. Well, first of all, you can only deal with a bunch, a very small bunch of distributions, the standard normal, student, chi-squared, and so on and so forth, which is enough to do a lot of statistics if you work in a frequentist framework, but not if you believe in Bayesian statistics, because in Bayesian statistics you have a prior distribution on how things look to you, but after that you have to change your belief and incorporate the data, and as a result, each time you get new data, you get a new distribution, generally speaking. So this means that you cannot deal with tables, because you know what data are going to appear in your case. So this has an implication that Bayesian statistics is only possible if you have computers. Before computers were widely available, this approach via table really made Bayesian inference out of the question. And also, but this is less important, that the class of integrands is also restricted. So this was for univariate distributions, for distributions in one dimension, but of course, oftentimes we need to have probability distributions in RD, and in many applications D could be 1,000 or 10,000 or even more. For instance, now you have the probability of your variable being in a set omega, and you see immediately that those probabilities cannot even be tabulated. In one dimension you can say probability here, there, but as soon as you are in two dimensions and you have different domains, you cannot even make tables. But it's even worse, because conventional cubature rules cannot be used to compute those integrals if you work in lots of dimensions. Just to give you an example, if you have quadrature in an interval and you put 3 points, even if you use a Gaussian rule or something very sophisticated, the result cannot be expected to be very accurate. But then you move to 10 variable to 10 variables, then you would need 6,000 function evaluations for such a coarse integration. And if you move to r to the power of 20, then you need in excess of 3 billion function evaluations. This means that this approach of a conventional quadrature is out of the question. So this is what Bellman, as is well known, called the curse of dimensionality. So one has to look for alternative ways of computing integrals or expectations. And of course, this is Monte Carlo. So the basic idea is that under fairly general assumptions, the number that you want to compute is the limit of a random sequence. So you generate random variables x1 to xn, independent, and each having density rho, and you take the average, and this thing will very approximately be the integral you want to compute. So this gives you this recipe to approximate the integral. And for those of you that are numerical analysts, this is like a ridiculous quadrature rule, because if you use Gaussian quadrature or other forms of sophisticated quadrature, you see that a lot of ingenuity and a lot of mathematics goes into computing the weights. But here, all your function evaluations carry the same weight. So this is clever because you choose to put your points, your abscissa points, your quadrature points, at locations where the density is big, and not to put them at locations where the density is low. But otherwise, it's very unsophisticated. So the simplest case of this is when you have the unit square and you have a region here, and then you integrate the indicator of this region. Then, of course, the integral is just the area. So this is a way to compute the area of this domain omega. And then what you have to do is like take darts and throw many darts uniformly to your unit square, and to count how many of them fall or hit into omega. So this will estimate the area. Well, it's not difficult to prove that if you do that, the quadrature error goes to 0 as you throw more and more darts, as the square 1 over the square root of n. So this just tells you that this is something to do with computers. You need to throw maybe 10,000 or 100,000 to have any accuracy in your estimate. So this is very different from conventional quadrature. But the good news about this is that this estimate holds regardless of the dimension d, works in 2D, but also in R 10,000, no problem, and is not affected in any way by the lack of smoothness of your integrand. So this is not something you want to use for in a low dimension and for a smooth integrand, because then you work a lot, but is something that will always work when other alternatives don't. But there's a problem. How do I generate the random samples? Well, your computer surely has a random number generator from the normal distribution or the uniform distribution, but if the thing is more complicated, then this is not in the computer. And then there's an alternative, and this is to realize that the law of large numbers that I've written there will also hold not only if I assume that the random variables are pairwise are independent, but if they form a Markov chain. So for those of you who are not experts in probability, a Markov chain means that the m plus first random variable is not independent of xn, depends on xn, but only depends on xn, not on the past, but is such that, loosely speaking, if xn has probability distribution rho, the recipe by which you generate the next one ensures that this will also have the distribution you have. And then the wonderful thing is that in a very, very important paper in 1953, those 5 authors, so 1 author and 2 married couples, they show that it is really possible to generate functions, samples from an arbitrary distribution. So no matter how complicated your distribution, how many, what the dimensionality, you will always, if you follow this recipe, you will always be able to compute this, thereby approximating your integral. So this is the so-called random walk metropolis algorithm. There's a parameter, so I choose a value of h, that is step length, and assume that this floor is R2, and I have the distribution in R2, so I'm here at this point. This is my current location, xn, and to find the next location, what I do is I choose randomly a normal random variable. There's a direction and a distance to travel, and this has unit variance, and I multiply by h, so h really measures the length of my step, and so I'm here, and I take a step there randomly. So sometimes I will go there, or sometimes I will go that way and that way. So if I only had that, you will see that I would keep moving on this floor, and I will more or less be all over the place until I hit the wall here. But then the cleverness of the metropolis algorithm is that there's an accept-reject mechanism. So you draw a random variable between 0 and 1 from a uniform distribution, and then you compute the ratio of the probability of the location I was at in the past and the probability at the new location. If this is bigger than un, this means that, roughly speaking, I'm offered to go to a place with more probability, then I will go there, and the next step of the change will be the new place. But if I'm offered to go to a place of low probability, then sometimes I will go, but by and large I will tend to stay put where I stay. And then you say that a rejection has been taking place. And it's not difficult to show that if you impose this rule, my locations will be distributed exactly according to the function rho. So that in the long run, I mean, the number of times that I'm at a given location will be proportional to the density, my target density, the density I want to sample with. So the beauty of this is that it's an algorithm that is very simple. You have to use it in a computer. You couldn't use this without a computer. but works for any integrand, any distribution functions, and any number of dimensions. Of course, nothing is perfect, and the random variables I generate, as with any other Markov chain, are correlated. And then this means that my samples are almost, they are correlated. So to speak, I'm like repeating the same locations, so the integral is not very accurate. And then here, there's like a dilemma. I'm here. And if my time step is very big, typically I go to a place with very low probability, because even if you are in R1000, probability is only 100%. So it's limited. So most places in high dimensions have very little probability. So typically, if I leave the current location, I go to another place very far away, I will hit a place with no probability, I will be rejected, the step will be rejected, and I'll stay put at my previous location. And I repeat the quadrature point, which is not very good. On the other hand, if I'm not very ambitious and I take very small steps so that my proposal is close to my previous location, then you see that typically I can hope to be accepted, but the problem is that the samples will again be very correlated, because my new sample is very close to my old to my old sample. So this a very interesting paper in '97 in fact shows that if you go to high dimensions, this step length h has to be chosen proportional to 1 over d. You need order d squared work to make order 1 moves, as this is as d goes to infinity. And the exploration of the state space is optimal if you see that you are accepted 23% of the times. And this is regardless of the suitable product hypothesis of the distribution. So this algorithm always works, and please note that you only use the target, this rho that you want is the weight in your integral. You only use it in the accept-reject mechanism. So I'm here, and there's a proposal to go somewhere to look for other points, but the points I want to look for are completely independent of my target. So the idea is to incorporate knowledge of the target into my proposal mechanism, with the hope of having more chances of having my proposals accepted. Well, there are very many ways of doing that, and the one that will occupy us here is the so-called hybrid Monte Carlo method. But this is only one algorithm among hundreds of others that are studied in statistics. So this algorithm was introduced in the physics literature by people in Edinburgh. There's a D missing there, right? And at the beginning of this century, Neil made it known to the statistics community. People in statistics thought that this H, which the physicist meant hybrid, means Hamiltonian. So people now in statistics call it the Hamiltonian Monte Carlo method. It's okay. And this method comes with a slogan. This is a method that has the capability of having proposals. So rather than moving just this, you can have proposals where you can go very, very far away from your current location. And yet, you will be accepted with high probability. So, so this is the aim of the algorithm, not that it always delivers what it promises. So I'm going to explain how this algorithm works, but to do this, I need to take some detours. So the first detour is a detour on statistical physics. So this is Newton's second Newton law for a conservative system, the masses, the positions, to dot the accelerations, and the forces are the negative gradient of a potential. And as is well known, the solutions of these second-order differential equations preserve this, which is mass velocity squared and halved. So there is the kinetic energy and the potential energy. So this system will evolve while conserving energy. So this is all very nice, but now we look for a more complicated setting. Now we put the system not in isolation, but in a heat bath. For instance, you can think of a molecule that is inside a human body or the body of a cat or another animal. So this molecule, if it's inside the body, will be hit by molecules of water. And each time this is hit by a molecule of water, energy will be transferred from the protein, say, to the water, from the water to the protein. And now the number of times that this happens to this molecule is staggering. I mean, this Avogadro's number and the velocity of the molecules of water makes that the number of times those hits take place is beyond imagination. So this cannot be really modeled by a differential equation. You have to have a statistical description of this. And this is the aim of statistical physics, as developed by Maxwell and Boltzmann and Gibbs and others. So our system that we described with Newton's second law cannot to be put into statistical framework. You first need to rewrite it in Hamiltonian form. You can use Newtonian mechanics and Lagrangian mechanics, but if you want to do statistical physics or quantum physics, you need first to rewrite everything in Hamiltonian form. As you know, this consists of introducing a new independent variable, which is the momentum, the mass times velocity, and then this is Newton's law written as a first-order system. But the beauty here is that it's very symmetric, because you can write those equations in this form, where h is just the Hamiltonian, which is the energy. And then if you go to a statistical mechanics textbook, you will see that our molecule, the configuration of the molecule, will evolve in such a way that this measure with density, the exponential of minus beta times the Hamiltonian, will be conserved. Okay? So if I look at this, what is called in physics the canonical distribution, because h is the sum of a kinetic and a potential part, this exponential is the product of two functions, which two densities. One is the density for the momenta, and the other is the density of the configuration. And because it's a product structure, they are stochastically independent. So what happens to the configuration doesn't affect what happens to the momentum. They go independently, stochastically. If we look at the density for the momenta, you see that it has this form. So this is quadratic, so the exponential or something that is a quadratic is a Gaussian distribution, maybe in more than one dimension, so a kind of Gaussian bell-shaped curved, and this was introduced before by Maxwell. And if you compare this with your textbook about Gaussian densities, you see that if the density is this, then the average kinetic energy is d times 1 over 2 beta. And this is really the definition of temperature in statistical physics. So 1 over beta is twice the average kinetic energy per degree of freedom. So this is what really means that that today we have 10 degrees and before we had minus 3 degrees. This really means that the oxygen in the air has now more kinetic energy on average than it had last week. And the positions have this density discovered by Boltzmann. So the density is of this form. So you see if the potential energy is very high, so this is very negative and the exponential is very small, so the system doesn't like to be at places with a very high potential energy. And as you decrease the temperature, the more the system will like to go to locations with low potential energy. So as the limit, as the temperature, the absolute temperature goes to 0, you will find your system almost with 100% sure at the minimum potential energy. So now a second small detour, and this is more related to this semester here. Again, a Hamiltonian system. This is the solution flow, so this means that this is the value at time t of the solution that has initial conditions q and t. So if you look at this as q and p being fixed, then this is just the solution to your Hamiltonian dynamics. But here we are more interested in fixing the value of t at a given time and seeing how this varies as a function of the initial configuration and the initial momentum. And due to this beautiful symmetric structure of the Hamiltonian system, the flow also has important symmetries. The first one is the so-called Liouville theorem, is that when you transform your initial condition to your final condition, the volume in phase space is conserved. Have initial conditions, they evolve, they go there, but the volume will be the same. In fact, there's a stronger property called symplecticness that goes back to what Poincaré called the integral invariance of the system. There's also preservation of energy. The energy at the initial condition is the same as the solution after t, and because of this special form of the Hamiltonian, the flow is also time reversible. So I start from a configuration with a given velocity. After 1 second, I'm at q star p star. This means that if I started at q star and negated the velocity, I would land up at the initial point with a negated velocity. Okay, so if this stays here, and in 1 second comes there. If I start from there, but I give it a negative velocity, it will go to the initial condition, but with the opposite velocity. And as an implication of those two properties, this Hamiltonian dynamics exactly conserves the canonical distribution, the distribution that our protein in the cell obeys. This is because by conservation of volume, this is conserved, but then the numerical value of h is also conserved, so this function is also conserved, and by implication, we have this conservation of the canonical measure. So, so after this detour, statistical mechanics, and detour number 2 on Hamiltonian equations, I go back to the Hamiltonian Monte Carlo method. So remember, our aim now is to construct a Markov chain that preserves rho, right, and to be used for this central law of that large number to approximate the integrals. So here's a way to construct such a Markov chain that will preserve our target density. So the first thing is where I had x for the variable in the first slides, I call this q. I remember when I first started teaching, I had a colleague, and this colleague was writing some exercises for the students. And I asked her, now this differential equation, how do you solve it? And then she says, well, here I need to do a change of variable, so that rho I will call hereafter y. And then I told her, but this is not a change of variables. And then she says, yes, but students get confused if the unknown function is called something else rather than rho, rather than y. So they always need to start with y. So for Hamiltonian dynamics, we always need a q. So what was before x, I need to call q. But this is not a change of variables. So this rho is the target, the thing I want to sample with. And my target, rho of x, that has become rho of q, I will write as the exponential of something. So this is the definition of a v. I can always do this because this is non-negative, so I can always take the logarithm and put a minus sign there. And hereafter, even if this density has nothing to do with mechanics or is something from some Bayesian inference, nothing to do with mechanics, I will refer to this V that I've constructed as the potential energy. So now I have a potential energy, and I introduced auxiliary variables P that we'll call the momentum. I consider this Hamiltonian function and the Hamiltonian dynamics. And then the recipe to construct the Markov chain is as follows. This Qn is my current location, the point where I'm at, where I want to sample. So I generate a momentum from this distribution. For simplicity, the mass matrix I put to the identity, and I omit this beta factor of the temperature. Well, this I can do because this is a Gaussian, standard Gaussian distribution, and my computer, all computers, have random number generators to give me this Pn. So this is my current location. I generate this from my computer. I put this as an initial condition, and I let it evolve with the Hamiltonian dynamics. It will go somewhere. So at the end, the solution will be Qn plus 1 and P tilde. So this P tilde I discard, and this Qn plus 1 will be my next location, okay? So I'm at location Q. I draw a velocity. With this position and velocity, this will evolve. I go somewhere else. The velocity I discard, and I look at the position, and this is my next location for the Markov chain. And you see that this has the magic property that this distribution is preserved. This is what I told you before. The Hamiltonian dynamics preserves exactly the canonical distribution. If I marginalize, so I only look at the Q, it will preserve exactly this one. So this means that I've got a Markov chain for which my target, e to the minus v, is an invariant probability. Well, this would be too simple to be true, and of course here the problem is that the Hamiltonian dynamics, going from the initial condition to the final position, well, this is not available in closed form. It's only available in trivial cases, but in those cases maybe it's also possible to use my computer directly to generate the random numbers. So what do? We have initial condition, we want to go there, we don't know the exact solution, so we use a numerical method to simulate the system of differential equations. So I have to choose a step length for my integration, and this will be. But if I want that my distribution is preserved by the numerical integrator, what do I need? I told you that the Hamiltonian dynamics preserves my distribution because of two things. It is volume preserving, to conserve the dq dp, and also conserves the value, the exact value of the Hamiltonian. So I would need to be happy a numerical method that has those two properties, those two geometric properties. And this is where this research fits with a geometric integration. Okay, in 1997, so a long time ago, in those days, every 10 years they had a conference called the State of the Art in Numerical Analysis, and then they produced a book, and the speakers, there was a conference, the speakers had to say what were the most important things in the last 10 years. And I was invited to do such a contribution. And then I had the idea, say, how could I call what has been happening here? And I came up with this term, geometric integration. Because what I perceived as being new in 1997 in ODEs is that before you didn't pay much attention to whether your numerical integrator preserved invariants or geometric properties of the system being integrated. And in the 90s there was a big trend in that direction. So I came up with this term. And unfortunately, one of the very first results in geometric integration due to Marsden is that it's impossible to have an integrator that simultaneously preserves volume and energy. So we couldn't integrate this. But then we have to combine this idea with an accept-reject mechanism as Metropolis is. So we are going to use this Hamiltonian dynamics because it's impossible to have the properties of conservation of energy and conservation of volume. The measure, the probability I want to sample with will not be conserved exactly, but I'm going to make up for that numerical error in the integration by imposing an accept-reject mechanism that will ensure that after this mechanism, rho will be exactly preserved. Okay, so I finally arrived to a description of the algorithm. So the recipe is as follows: Qn is my current location. As before, I generate a velocity. I can do this as before. Now I integrate numerically, and I go to a place that I call Q star and P hat, P tilde. This P tilde I will discard eventually, but now this Q star, I'm not going to always accept it. I'm going to compute this quantity, and with this probability I will set Qn plus 1 equals to Q star. So I will move, but if I reject as before, I will stay put. So this is the mechanism. Now the first thing to observe is that, maybe I go back here, this thing in the exponent is my initial condition. I integrate numerically, come here. This is the difference in energy between the end point of the numerical integration and the starting point. But if the integration were exact, because Hamiltonian dynamics conserves energy, those two things would be equal. And if I use any sensible, this means any convergent integrator, those two things will come arbitrarily close. So this means that by taking my time step very small or sufficiently small, I can bring my acceptance probability arbitrarily close to 100%. So this is an algorithm that enables me to go very far away and yet ensures that once I'm there, I will be accepted with a high probability. And for this semester or program or whatever it's called, the most important thing of the talk is what's written in red there. is that this only works if your integrator preserves volume and is time reversible. It has some geometric properties. So here's an instance where geometric integration is not a choice. It's not you say, okay, I get nicer pictures if I do this than if I use a non-symplectic. Here, if you don't have those properties, those geometric properties, you are out of business. What you get will not be samples from your target distribution. You have no choice. You have to do this. So the second bullet is the slogan of the algorithm. You can go very far away and yet be accepted with a high probability. Now, for those of you who have been here for a long time, I gave a seminar here maybe in September about how to integrate these dynamics for the Hamiltonian Monte Carlo. And there I showed that people only use this what's so-called leapfrog algorithm. In statistics they call it leapfrog, in molecular dynamics Verlet, but it could be Sturmer algorithm. And this is everything people use in practice because it's simple to code and is time reversible and volume preserving. But this is not the best choice. You can do 3 times better by switching to different algorithms that are constructed specifically for the HMC algorithm. So this is something I've done a lot of work with a number of co-authors. And before I retire, which is not very far in the future, my aim in mathematics is to persuade people that they should leave this leapfrog, and it's very easy to code, and they should move to this other kind of integrator that in the same amount of computational time will deliver maybe 3 times as many good samples as leapfrog. But this is my crusade until I retire. This is the last slide. Before I quoted a very unbelievable result that for the Metropolis algorithm there's a magic number which is 23%, and if when you sample you see that you are accepted 23% of the time, then this is your sampling is optimal. Well, such a result also holds for the hybrid Monte Carlo. There's this paper there, and we showed that here there's also a magic number that is 65%, regardless of the distribution being sampled. And when you compare with Metropolis, you can see that those numbers are also better, because in Metropolis this H has to be chosen proportional to 1/d. So each time you double the dimension, your step size has to be halved, and each time you double the dimension, you have to work 4 times as much, and those numbers are better for those scaling numbers are better for the hybrid Monte Carlo. So the work to traverse a distance in state space of order 1 is d to the 5/4 rather than d to the 2, and H has maybe chosen, as the problem increases, the step size in your algorithm has to decrease, but is very mightily. So I thank you very much for your attention, and this is all I wanted to say. Thank you very much for coming.
Thank you very much indeed. It was very clear. Even after flying the whole night from Hong Kong, it was still very clear. So we have time for questions and observations.
So what would you recommend when your row has zeros?
Sorry?
When your function row you want to sample, what do you do when it has zeros?
Well, there are various things you can do, but you can simply assume that the potential is infinity there to exclude those regions.
And also for your integration?
Yep.
It's okay?
But there are other ways, other things more sophisticated that you could do.
If you just zero in an area and then starts again, then you never get to that area, is that so?
Yeah, but this could happen, but this is, I think, is a disease that is shared by all Markov chain Monte Carlo methods, that you can never be sure that there are not other regions in state space far away from what you have seen that has some significant probability. So I wouldn't think that this is a particular bad feature of this algorithm. It's a difficulty with all Markov chain Monte Carlo algorithms. So you tend to think that what you've seen so far is the only thing that exists.
In similar terms to how you explain it, could you comment on the volume preservation necessity so that you can implement it? So why do you need that? I mean, I understand that when you introduce Hamiltonian,
Yeah.
and I also understand that you don't really need to preserve the Hamiltonian. So then why volume? When is it important?
Yeah, well, I mean, so it's important. Well, it could be important in two ways. One is simpler, and the other is maybe more sophisticated. And I'm going to try to explain both. The simple one is that you have this accept-reject rule. So at the end of my integration leg, I have to compute the Hamiltonian, and I have to compare. And this is simple. This doesn't involve a lot of new computations. Now, to prove that if you do this, you actually, your algorithm exactly preserves rho, then you need, when you carry out the algebra, you need that. If this doesn't happen, so if volume is not preserved exactly, you could still use the algorithm, but then you have to change the accept-reject rule, right? And then the accept-reject rule may become very complicated because depending on the particular circumstances, but it could be the case that while here it only depends on the initial and final point, you could need to carry out the Jacobian of the numerical method and integrate a variational equation, or so it becomes really very expensive and complicated. So this is one. Then the other thing is that what you need is volume preservation. But in practice, if you restrict your attention to usual schemes, the only way to achieve volume preservation is by imposing symplecticness of your algorithm. So you have to use a splitting algorithm or a partition Runge-Kutta, something that simultaneously to volume preservation as a bonus will give you symplecticness. And this is advantageous for Hamiltonian Monte Carlo, because then we know that energy will be preserved very accurately over very long times. So because you use that kind of integrator, it could be that this difference is very small, even if your point is very far away. So the symplecticness of the algorithm also helps in this different notion. But as with anything in mathematics, there have been papers written on algorithms that don't preserve volume exactly, and so on. So
preconditioning, for instance.
Sorry?
Preconditioning, that would have to do with the
Yep.
with volume preserving, right?
Yes, I see correctly. You choose at each step a completely new momentum Pm. But I mean, as you would say that you would continue in a certain direction to law a bit more space and not be stuck, wouldn't it be natural to somehow make Pn depend on the previous momentum?
Yes, you're right. But this was proposed by a physicist called Horowitz, and is called the generalized Hamiltonian Monte Carlo, and it works like this. So you start here, you integrate here, and then you've got Q, and let's call Q star and P star. And say I accept. If I accept, rather than discarding this one, my initial condition for the next will be this Q star, because I've accepted. And then the initial condition to start from here will be a combination of this at the end and something that I draw. And I put coefficients here, let's call them gamma and 1 minus gamma. And those coefficients have to be chosen, that if this comes from the Maxwell distribution and this comes from the Maxwell distribution, this comes from the Maxwell distribution, okay? And as you said, this ensures, you say, if this gamma here is close to 1, this means that at the next integration leg, I will start from a direction that is almost the direction I was coming at. It will be a small variation. You need always to have gamma to bring in a new draw, because if you don't keep a new draw, you keep always at the same energy level. So you have to really randomize your velocity, because you want to go far away, and then you need a big momentum. But rather than throwing away completely the velocity that maybe was a good velocity for your problem, you make a mix of this with a little that you can look at noise that will allow you to change from one surface of equal Hamiltonian to the next surfaces, so that you, at the end of the day, you explore all energy levels that may be present or are present in your problem. See, this man is Horowitz. And it's an old paper. It's more than 20 years old.
Now, you mentioned your future life project to persuade people not to use Sturm overlay but other methods. So, do you mean simply higher order symplectic methods?
No.
Or something specific?
No. I mean, people have tried higher order methods, but I think there's no future in that, because the integration needn't be very accurate. So even if you're, I don't know this by heart, but I think even if your energy error is 1 unit, you are still accepted with, I think, a probability like it's maybe 25%. So here is a regime that is very difficult for numerical mathematics, because you really work with errors that are 1.5 is not 10 to the minus 7 or 10 to the minus 8. And as soon as you are at that level of very, very inaccurate integrations, then unfortunately analysis has very little to say. Most of things we know about numerical integration are based on the behavior as delta t goes to 0, in particular the notion of order. So I don't need a method that if delta t were very small would be very accurate. On the contrary, I need a method that if delta t is very large, works well. And well, this is the kind of idea that we are putting in our work. Yeah, but all new integrators that we are coming up with, well, it doesn't mean that I'm coming up with a new integrator every month. I mean, say a couple of integrators that we've identified as being very beneficial in this context, both are second order. And all the others we've tried are all second order, because you try fourth order or sixth order and so on, they're no good. They're no good, because this means that if your acceptance probability was, when it was already 99%, you go to 100%. but this is of no consequence. What I want is a method that accepts maybe 40% or 50%, even if delta t is very large, so that I can work very little to go from A to B.
Okay. Are there any further questions? Okay, so let us thank